Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, good morning, everybody. Are we on? Yep, I think so. I'm Stuart Townsley. I'm just the host for this session. I'll hand over quickly to Seth Goldstein. Professor Seth Goldstein has been one of the most stimulating professors I've worked with over the past year. It's been a real privilege with the amount of interesting things that he gets up to. He describes his research domain as systems nanotechnology. And we're going to get two tastes of this, both today with this talk, the Brain in the Bottle talk, and then tomorrow he'll talk about some of his other work in the same sort of area, but a different context. So please come back if you enjoy this talk tomorrow at the same time, in the same room. So without further ado, let me hand over to Seth.
Thank you, Stuart. Thank you for having me. This is a particularly good place to give this talk because Microsoft paid for some of this research. Thank you. And so this is sort of a brief introduction and motivation because I actually haven't talked about this here before, and also a little bit of a status report about where we are. And the person who's doing most of the work is Felipe Trevisan, who is the graduate student that's being co-advised by myself and Carlos Gestrin. This is a plot I'm sure everyone here has seen from Hans Moravec that basically tries to associate some kind of computational power to various biological organisms. And Hans and others have basically sort of calculated that the human brain has the equivalent computational power of about 10 to the 8 MIPS, or 10 to the 14 operations per second. I'm going to explain why I think that's a really terrible metric, but it motivated me to think about, maybe one of the reasons why AI is really hard is we just don't have enough computational power. So is it possible to build a system today that would be a tool for AI researchers, among others, but that was the original motivation, that would enable or facilitate AI research and understanding the brain. So what I would like to propose is to build something to that scale, that physical scale, that little box, maybe a meter or two, 1 or 2 cubic meters, that has about an order of magnitude more computational power than at least what people estimate the human brain has. Okay, so let me give you some brain facts in case you don't know. And by the way, it's a small group. I'm happy to be interrupted at any time. So the brain's not that heavy. It doesn't take up that much space. It doesn't use that much energy. And it crams a lot of stuff in there, about 10 to the 11 neurons. To me, the most interesting sort of brain fact is the number of connections per neuron, the number of synapses. So basically, every neuron is connected to about 10 to the 4, 10 to the 5 synapses. On average, some areas of the brain are much richer than that, and some are significantly poorer, but this is a good average, and so we'd like to target something that has on the order of 10 to the 14 connections. And these things are really slow, 10 hertz about, and yet it's sort of pretty amazing. So you can use various methods to calculate what the computational power is. You can look at the capacitance of the neurons, the speed of the synapse, the amount of energy being used. You can look at the visual system, which we understand really well, compare it to the number of ops it takes to do vision on a processor and extrapolate. Anyway, about 10 to the 8 MIPS is what you get. Some people argue this is way underneath it if you sort of think about each protein as a processor, but I think that's probably a bit extreme. Okay, but I think it's a bad metric. Okay, and so the question I have is, what is the best sort of system architecture to think about? So I want a metric to evaluate an architecture that would facilitate AI research and research that would help us understand how the brain works. Okay, and I think that just getting more MIPS and flops is not the answer. Buying 50 or 100 or 1,000 blue gene L's or P's or whatever they're up to now is probably not going to answer the problem. So my thesis is that while MIPS and flops are good, connectivity is better. In order to evaluate that thesis, we need to really build this machine. And I'll talk a little bit more about that later. So today, in June, I guess, the blue gene down at Los Alamos got to about a petaflop, which is about 10 to the 6 megaflops. And basically everybody focuses on these. This thing is a Roadrunner, so we would need about 10 to the 4 of these to get the same number of ops per second. You couldn't use all those floating point ops, but that's the way they get their ops. But I think what's really important is the connectivity. So this blue gene, the Roadrunner, is made up of 17 what they call computational units or computer units or something like that. And each one has a 288 port InfiniBand. So in other words, it's very connectivity poor, at least between these big cabinets. And even inside the architecture, if you look at it, it's very connectivity poor. Sort of the message volume is small. You know, we think about balancing machines in terms of how much memory for each, you know, gigahertz or megahertz or whatever it is. And there ought to be something like that to say, given certain processing, how much connectivity would we like to have. Okay, so in the important neurons, it's about 10 to the 5 connections for each neuron, so it's about 10 to the 14. And the other thing is we probably can't afford to just get 1,000 of these blue genes to get us there, because this one takes about 4 megawatts. So 4 gigawatts would sort of be problematic. And this is the most power efficient supercomputer that exists by a factor of like 3 or 4. Okay, and the next 4 down the list are all by IBM too, in terms of power efficiency. Okay, so what I want to do is build what I call a brain in a bottle, just because it sounds good. It's actually in a box, but something that's fairly small, and focus on the connectivity, okay, and scaling. So one of the sort of paths on how I got here is I'm very interested in sort of stochastic processes, particularly in manufacturing. And so I'm looking at something that's much, much less expensive than the blue gene, which is highly engineered. So what I want to do is sort of build these very simple processors. Let's say they're packaged in a sphere. I'll explain how that packaging works in a little bit. And then you sort of drop them in the box or the bottle. And then that's your system. Okay, and so somehow that makes it, you know, sort of robust, because the construction method requires robustness. It doesn't work at all if it's not robust. And makes it fairly inexpensive and easier to scale. You just drop more nodes in. And so I'm going to use this sort of soccer ball as an icon for my processor. Think of it being about 1 millimeter in diameter or less. Right now, I think we could probably make these easily today at about 600 microns in diameter. And then there's going to be some wires, and I'll explain how those wires work later. Okay? So if I really want to put 1 billion of them in there, then just for packing to make it easier, I probably need 2 cubic meters. If I actually did it right, I could get it into a cubic meter. But it's about a cubic meter. Okay? So I'm going to explain how to build these spheres first, and then I'm going to go through some numbers to convince you that this is reasonable, and I'll talk about the networking and then some algorithms. Yes?
So I have a question. So back 2 slides, I mean, you set up this sort of straw man of connectivity,
yeah,
where the InfiniBand is only 288 ports, but I mean, it's much faster, obviously, than the Snap connections. And I mean, virtually, each thing can talk to each other thing, you know, at 10 hertz or whatever, probably. So is there a reason you didn't want to pursue this type of architecture, even though I mean, effectively, you still can get that kind of connectivity, just really slowly, I guess?
So I guess at 10 hertz, the thing is we have to do a lot of other simulations too. I haven't done the analysis that says if I want to give, like if I want to divide this up into, I mean obviously this isn't the right way to use this architecture, but if I wanted to divide this up in 10 to the 11 processes that were all talking to each other, what kind of message volume could I sustain? I probably should. I think it's pretty poor, but I don't know. That's a good thing to do.
I agree that what you're doing is a lot more interesting than that, but
right. Well, that's partly why. Yeah. So I'll do that calculation and I'll get back to you. That's a good calculation for me to do. There's nothing you can get around this. Yeah. And I also, you know, if this is a scalable technology, so I'd like to put a small brain on my desk, and so we could do that. So that's the other thing. Okay. So let me explain how we're going to make these things, and actually, shameless plug for tomorrow, this same basic technology is going to work for Claytronics as well. So I want to make this as inexpensive and as small and lightweight as possible. So for thermal properties, I want to really sort of do away with packages if I can. So what I'd like to do is sort of print my chip on some basic silicon and then make that the package. So somehow I've got to turn this flat thing into a sphere just because it's easier to think about spheres. We could think about dies, but I don't know how we're going to get the network that way. So the thing is that a thin film of silicon is actually flexible. It's not rigid. And so if I just take the silicon on top of this silicon on insulator, on top of the insulator on this typical SOI wafer, it's very, very thin. And actually, you can engineer the stresses. And this is not my idea. This is Rob Reed's idea from the Air Force Research Lab. Instead of printing your die on some kind of rectangular form, print it in this flower shape. You can engineer the stresses here so that when you get rid of that insulator and you are left with this very thin silicon, it should, so we're going to put our die on here. It should curl up into a sphere. And actually, we're in the process of making some of these. This is actually a really old picture. But we can actually make, Rob can make, and my graduate student, I can't make it, but we can make these little spheres. And there's, in a 1 millimeter diameter, assuming we can close this space up, we have enough area here to put a lot of stuff here, right? It's about it's about 2 square millimeters of surface area that we can use. Okay, so this is our little sphere. And so in a 90 nanometer process, so this is sort of ancient already, the kind of stuff you can imagine putting in that area would be something like an ARM7, a quarter of a megabyte of memory. So this is a little underpowered in terms of the amount of memory we have. And then all the support circuits you would need to distribute power, which I'll explain how that's done in a minute. And we fill the middle, we curl it around, let's say, a supercapacitor, which has the energy for about 1 billion instructions, and then they transfer energy between each other. Okay? And so these are today's numbers. These energy numbers make this thing run a little hot, and I'll explain how we're going to get it cooler. But if we go down to, let's say, 45 nanometer process, then we have a lot of room for extra memory, for instance. I don't think we need any more processing in this. So let me talk about the power a little bit. I think partly one of the things that I like about this project is it motivates a bunch of other research as well. So to really scale this up, we probably need to reduce the power. And we have to consider 2 things, the dynamic power and the static power. And once we get down to the 45 nanometer node or below, the sort of leakage current, the static power becomes a serious consideration. So there's a couple of ways we can do that. One is we can use less hefty processors than an ARM7 and put a bunch of them on each one of these dies. So essentially just use parallelism to slow the clock rate down. That allows us to lower the voltage. And the other is to use better circuits. Before I started doing this kind of stuff, I spent a lot of time thinking about asynchronous circuits, and they are they're less power hungry. Yes?
I was expecting, I guess, to write joules per instruction. You write watts per instruction. Does that mean something?
Well, in the way the ARM7 works, when they quote it on their data sheet, they say you can, depending on how fast you want to run it, it's going to be a certain number of, microwatts per megahertz. Okay, and these are basically all single instruction issue, one instruction per hertz. But I will start talking about joules, but picojoules per instruction. So there's lots of circuit techniques around, and it's not just for building, large-scale systems that people care about power. Everyone cares about power, as I'm sure you all know. And so there's lots of standard CMOS low-power stuff. There's lots of asynchronous circuits. I think exploring reversible computing is interesting, but we don't really need it. So for instance, if we just stay on this industry trend, so for instance, Todd Austin at Michigan has this processor that he fabbed at 130 nanometers, and it's 0.6 picojoules per instruction. So that's about 3 orders of magnitude better than what people standard get today. If you include the memory in this, that's 3 picojoules per instruction. And there's no reason why we can't get to about 1/10 of a picojoule per instruction. This is all well within the realm. And this is at 130 nanometers, so we can shrink this significantly. And so if we do get to 0.1 picojoule per instruction, then 10 to the 9 MIPS, so that would be 1 order of magnitude more than what Hans says is the human brain, would be about 100 watts. Yeah.
That includes static leakage?
Yeah. This is complete, this is static and dynamic. Of course, at 130 nanometers, the static is a smaller component. But if you look at the curves, you can see that as you boost up the frequency, so the static is not as much of a proportion as it would be today. And so that's certainly something we'd have to consider. So when we go down to 45 nanometers, it's not going to get 4 times better. We're not going to win that way. Maybe it'll get twice as good.
And for the brains 10 to the 8 nits, how many watts is it taking?
My brain? 25 watts. Approximately. Well, I'll talk about cooling in a second. Let me just talk about how we're going to deliver power to this, because we've got all of these things thrown in this box. There's no power plugs for each unit. And we actually need this sort of headroom. So 100 watts from computing and communicating is going to require more power dissipation, because we've got to distribute the power. The method we're using is not that efficient. But imagine that we have these spheres and they're in contact with each other. So we could potentially set up some kind of communication path that way. We're not going to actually do that. But if we put on the surface of the sphere, we coat it with a dielectric, and right under the surface we have metal plates. Then when two of these spheres come together, what we have is, let's say this is blue one is one sphere and the pink one is another sphere. The plates form these capacitors across that interface. So if I put an AC current on the blue guy, it's going to transfer a load over to the pink guy. Okay, so these guys are actually, they're far apart, but when they come together, they form this capacitor. And we have actually demonstrated this, so we can get this to work. So you can imagine I have power in one guy, I've got to get power to the next guy, and so I essentially send him a packet of power, and then he can continue to route that. And so the power distribution problem becomes this networking problem to make sure everybody's getting the right number of packets they need. And it's efficient enough that we won't spend all of our time just routing power. So the surface provides the initial thing, and then it sort of filters out through the rest. So this is just one scheme. There's other schemes that we could consider using. Okay, so so far we have like an examip machine, which is sort of cool, but the units only communicate locally with each other, and that's not very interesting. It takes a long time to go from one end of this machine to the other. Okay, and as I said, I think connectivity is the key thing that's my thesis anyway, for enabling this kind of research. So we're going to attach wires here that are about 10 diameters long, and where the sort of the basic unit here is the diameter of the processor. Okay, and these wires will be coated with a fairly resistive material. Okay, so when two wires cross and connect, they're going to create a highly resistive contact. Okay, but not so resistive, it's not a perfect insulator, that they can't actually, a signal on one will get transmitted to a signal on another one. So imagine here then that we have, let's say, these nodes, 4 nodes, A through D, and their wires are connecting at these big black blotches. We can engineer that resistive coating and the signal strength that we put on the wires so that we can choose whether or not, when a node puts a signal on this wire, it is successfully transmitted through 1 or 2 contact points. Okay? So the idea is to do it so that there's 2 contact points, that a signal put by A will be seen by B because there's 1 contact point. It'll be seen by C because that goes from A's wire to B's wire to C's wire, but it will not be seen by D. Okay, let me just illustrate this with a little graphic, right? So imagine I use an AC signal on A. It goes through this resistive coupling to B, the blue wire, and the amplitude of this signal gets shortened, and then it gets shortened some more, but it's still more signal than noise, and by the time it gets to the rest of the machine, it's basically just noise. Okay? So if we had sort of uniform 1 centimeter lengths and a uniform distribution, then every node, you can sort of just do the basic math, gets about 10 to the 6 neighbors.
Are you assuming that the wires are straight lines for that calculation?
Yeah, so it turns out I'm going to show you some real data in a second from our simulators. But 10 to the 5 is well within sort of stochastic process. Now, I don't really understand how to do this, so it could be that it's not, it might be 10 to the 4. I don't really know. If the wires are sort of, imagine that we start out the box as water, and we create hydrophobic wires, coat them hydrophobically. They're basically going to want to stick out. So as we drop these things in, the wires will mesh together. The ones on the bottom will be all sort of bad, but as you get in the middle, there's a lot of connectivity. Yes?
So you're relying on a purely random stochastic process?
Yes.
Two wires to connect, and if they're both hydrophobic or hydrophilic, they may have a repulsion.
No, if they're both hydrophobic, they're going to want to, if they're both hydrophilic, yeah, that's true, that's an issue. I hadn't thought about that. So there's going to be a lot of, there might be some repulsion, but we're going to need to sort of glue them down because I'm going to use the extra space in this box to pump coolant through it to keep them cool enough. And if I don't glue them down, they'll go all over the place. So the gluing, you can arrange it so that there are chemicals on here, and with small electrical contacts, we can essentially weld them together. And so the fact that they might not naturally want to stick together is probably okay. Yes?
So one of the things that you get in an actual biological brain is the ability to prune and regrow these connections and change the circuitry that way. Are you going to emulate this in software per se, or how are you looking at that aspect?
First step, do it in software. In the long run, and this is now, there's so many Grand Canyons I want you to jump over of believability here. So this would be like Grand Canyon number 2. But there are molecules that if they change their conformation, they change their conductivity, and you can change their conformation with high voltage differences, like rataxines, for instance. I don't know how familiar with this. Yeah.
The other one is, so you've got 10 diameters. One of the other things you get in the biological brain that's beneficial is these very long axon connections.
This is just to give you, this is a calculation you can do like with a pencil and paper. If I start making it a little harder, it is a little harder to actually figure it out. There's a mean distribution of 10 diameters. There'll be some wires that are shorter and some that are significantly longer. And actually what we've thought about is we can have 10 diameters worth of copper, think about it, as copper exposed, and then some insulator in between so you can sort of leapfrog around. Yeah. So these are all, to me, these are all like, second order bits. If we can get the basic thing to work, doing that stuff is quite easy.
Are you going to be generating more heat through power going through the resistors than you are through the processing of instructions?
You mean, am I going to be generating more heat and power going through the wires than I am going to be processing instructions? Probably.
Resistive connections.
Yeah, resistors, I see. Well, the whole process of doing the communication is going to be very power hungry. Let's say an order of magnitude more than the processing.
It just seems counterintuitive if you want to build a machine based on connectivity, that you choose a connectivity means that is...
I want as rich connectivity as I want, and I don't know how else to get it. One way to think about these things is it's sort of like anisotropic wireless. Essentially, these are like waveguides, right, that make, and I don't want it to be isotropic. I don't want to just talk to my neighbors. I want to be able to reach across large distances, and so this allows me to do that. If someone can come up with a better scheme, I'm not wedded to this scheme. This is just a straw man proposal that I think, if I do the SPICE simulations, it looks like it works, and the chemistry people say it's not completely far-fetched, and so. But I'd rather have a better scheme. This is going to be a little power hungry. Okay, so we had, with the help of you guys, we built a simulator to understand what the structure of this thing would be, and then to run our algorithms on it. So at the very beginning, we'd like to see what the structure of the wiring graph is and how the nodes get laid out. So what we do is we sort of simulate randomly dropping these nodes into a box, and then to see what the wiring graph is, we sort of voxelize this thing up into voxels that are significantly smaller than a diameter of a node, and run the wires through it in a random process. So the wire, enters this voxel and then comes out at some, it's a straight line in the voxel, but we can sort of, so it bends around and we can sort of simulate take at least a rough guess at what the structure of this thing would look like. In general, for all the simulations I'm going to show you here, all the wires are exactly 10D long and they're completely conductive. I mean, there's no insulator along any of that surface. Yeah.
You showed us before that you knew how to kind of make these spheres.
Yes.
Do you also know how to make these wires? Or did I miss
I know how to make the wires. Knowing how to put the wires on the spheres is still something of an issue.
So it's not just a question of etching out some kind of wire thing on the
No.
sphere edge. It's something more complex.
There's some things that we've been throwing around, but I don't have any good. I mean, they're sort of small, and how to actually attach the wires is a question. What I'd like to do is I'd like to grow them out of each sphere. That would be the best thing to do, because then but I don't know how to do that yet. I mean, there are ways that you can think about doing it.
I was thinking very much like the energetic growth you see on a rechargeable battery. Have you ever looked at that?
No.
So one of the things you run into with a NiCad battery in particular is as you're charging it, the act of charging it causes metal to migrate from the plate into the electrolyte.
Okay, so that general process I do understand.
Yeah, and eventually, you get a shorted cell.
Yeah,
over
so
time,
if you could think about electroplating these things, starting out with a seed. You could think about doing some kind of catalytic growth, like the way they grow nanotubes or silicon wires at the nanoscale. So there's lots of different things we could think of doing.
Yeah, it's the same similar process.
The first nanos, well, yeah. So anyway, so there are processes I can think about, but I'm not betting on any one in particular. Okay, so also all these numbers I'm going to show you are for something with 1 million processors. So we can't really simulate more than 1 million today, just because that's on like a 48 gigabyte machine. So if you guys want to give me some more memory, that would be good. Because we also run programs on each one of the nodes, so we need a fairly big system here. So for 1 million nodes with the wires about 10D, then most of the nodes have about 2,200, 2,400 neighbors. So that's a big set of neighbors, even curling around and doing that. And this is the number of unique neighbors they have. So the wires make lots and lots more contacts. There's a lot of redundancy in all of those connections that you have. And there's a fairly big distribution. And the problem with trying to really evaluate this scheme with just 1 million nodes is there's too many of them on the surface. What I'd like to do is actually do this thing for 1 million and then cut away the ones that are out there. The surface to volume ratio will be much smaller when we get to 1 billion nodes, for instance. But even so, the neighborhood size is pretty large, so that's good. If we look at the number, so a contact point is sort of a physical connection. A hop is a logical connection. And to get from one end of this box to another, it takes about takes about 12 hops. So this is just a picking pairs at random and seeing how many hops it takes to get from one to the other, and it's a cumulative distribution. So once we get to about 8 or 9 hops, almost everybody can communicate. Okay, that sort of makes sense. The wires are, if you sort of do what's up, you have lots of neighbors. You can always go in the direction you want to. The nodes are, the wires are when they're completely stretched out, are about 10 diameters. And the box here is like, I don't remember how big the box is. We could calculate it. That's 70 or 80 diameters or something like that.
This is assuming sort of global knowledge of how all the connectivity graph, so that you can find the optimum path between the two nodes.
Yeah, this is just, if I was doing the offline routing algorithm, how would I do it? Yeah, this is, I'm just characterizing the graph. Yeah. I'm going to do some more of that, but I'll show you the real stuff in a minute. Okay, so one of the big problems with this network, the big problem with this network, is the randomness is all good. I mean, is if I've got two nodes that are both sharing cross a single wire, they interfere with each other. It's like all the problems you have with wireless. Hidden receivers, hidden transmitters, all that kind of stuff. So either the communication is going to have to be fairly sparse or fairly smart. If it's sparse, you're okay, because there's not going to be a lot of people competing for it, or if you're smart. And one of the things that we haven't gotten to but is on our list is looking at things like Radhika's work on desynchronization. So you've got a bunch of nodes that are all sharing some communication bandwidth, and what you'd like to do is make sure everybody who wants to communicate, if there's k of those, they get 1/8 of the bandwidth. Okay? So, you know, you've got, let's say, 100,000 people sharing a wire. It's not quite that bad, but only like 50 or 1,000 of them want to communicate, so you'd like to get 1/50th or 1,000th of that bandwidth, not 1/1,000,000th of the bandwidth. You don't want to just do time division multiplexing in a stupid way. And this desync algorithm is very cool, and they sort of self-organize, and the speed with which people can join and leave and get their piece of the bandwidth they want is very fast. And the other thing that's nice about this algorithm, so you guys should invite her out here to give a talk, is that it uses constant memory. So memory is a big concern of ours, right? The nodes have very little memory. Okay, so I'm going to tell you how we're going to address that a little bit. So let me just show you, we built this tool that sort of visualized the simulated brain. We call it an fMRI tool, of course, because why, you know, we want to. Let's see, so I think this is the right video. And I'm supposed to go down here. Where am I supposed to go again? This thing here?
Yeah, the left one.
Okay. So what you're looking at is sort of the nodes and the wires. The nodes fade away a little bit. It's 3D, so you're not seeing all the way deep here. And this is running basically sort of a testing to get our basic, you know, A and B are neighbors. They're one hop away, and I want to get them to communicate. Every node is trying to send a message to every single neighbor that it has. And they're all doing it at the same time. So this is sort of worst case kind of scenario. When you see this rash of red break out, it's because two people are stomping on each other. When you see blue, it means the wires are being used to successfully transmit data, and if it's black, then there's nothing happening on that wire for a second. Okay, and so in the beginning, at the very beginning, everyone just doesn't know what to do. They stomp on each other, sort of the whole thing turns red, then the basic back-off algorithm starts to recover, and then you see patches of red and lots of blue, and that's basically the way this thing then runs until you get to the end. So it takes, I don't remember how long this takes to get everybody to have sent a message to everybody else. But it takes a reasonable amount of time, but not an ungodly amount. And of course, as you make progress and fewer people, you know, more people have actually satisfied the thing and then they're quiet, then it really speeds up towards the end. Yes?
Computational units, right?
Yeah, these are the nodes. They're much bigger than they look like.
So how did you decide upon the distribution during the simulation? I mean, how did you decide how to distribute?
We drop the nodes in randomly, using gravity to pack them, and then...
So you didn't try to make it uniform? I mean, it looks not uniform.
Right.
So you didn't try to do
No.
Why? Is it like...
I don't believe that we need to or want to. I mean, if we could actually... I mean, so if we didn't have the wires to contend with, then we could drop them in and sort of shake them and get them to form an absolute lattice, and that would be useful. But the wires are going to make that never happens, right? Because the wires are sitting there, the nodes are going to roll around, they're not going to... And I actually, the more space we have in there, the easier it is to cool, so I'm not upset about it. And a 2 cubic meter box is not that big. We'll be able to get many more than 1 billion nodes at 1 millimeter diameters. Okay, any other questions? This tool is totally great for trying to diagnose problems in a bug. Not that the algorithm isn't working, but it's too slow, and so you get to sort of visualize it and see it stays red for a really long time, or something like that. And you can sort of hone in on the spot that you want to focus on and try and figure out what the graph structure looks like, because it's just a lot of data. So it's not as much data as the people who are looking at a real brain have, but it's a lot of data. It's also fun to play with. Okay, so get rid of that. Okay. Oh, whoops. I'm now in the wrong mode here. Okay. So that's the basic communication. I'm assuming for my power and heat dissipation calculations that like 50% of the volume is in the spheres, 20% is in the wires, and the rest is left over for coolant that I'm going to pump through. And so if I use FC77 and like a commercial pump, I can totally keep this thing cool, getting about 10 to the 9 MIPS, so 1 order of magnitude more than the brain. And this is the completely commercial kind of pump that I can buy. So you could get it at least an order of magnitude better than that. If you're going to ask me, yeah.
With that much fluidic energy, won't your wire connectivity be strained? How do you keep wires connected?
Like I said, we're going to do these welds. Right. We're not going to just let them free float around because that wouldn't work. There's a lot of pressure coming through. Yes?
How do you exactly connect the wires to the spheres?
I don't know. That's the discussion we were having before. I'd like to grow them, but I don't know that exactly how to do that. No. You could do that, actually, but the connections would be very poor because then you have to capacitively couple or resistively couple directly from the node to the wire, and that might require us to lose a hop or have to use much more power. So I'd like it to be free, essentially, energetically, to go from the node to its first wire. Yes?
Using a conductive fluid.
The problem I have with that is that it's too isotropic. So everyone just gets to talk to their neighbors. You know, it just decays with the resistivity of the fluid. And that might be interesting, but I don't think it'll give us the interesting structure we want. Yes?
Well, slurry assembly may solve the problem with the wires connected to each other and wires connected to the
Slurry
spheres.
assembly? I don't know what that is.
Where you take a hydrophilic in a fluid,
Oh, yeah.
and they eventually, through geometry and the attraction process, can give a pretty good mechanical bond.
This is between wire and node.
You make sure there's a termination on the wire
Yeah,
that
I see.
mates to a.
Yeah, so that's a possible way to do it.
So
Yes.
in the brain, is the communication isotropic or anisotropic?
No, it's not isotropic. It's certainly not random, but it looks sort of random, right?
Some brains are more random.
Right. Different parts of the brain are more random than others, yes.
So in the brain there is some global signaling through like
Yes.
chemical, whatever, and your simulation, your drawing, whatever it was, video of the connectivity kind of having a rash and stuff made me think, would it be possible to have some sort of global signaling like, oh, slow down a little bit now because everyone's talking, okay, now you can speed up, or something, you might be able to sort of optimize a bit, like globally
It's possible.
adjusting. I mean, I don't know what kind of detectors you would need to, like, you'd have to maybe start manipulating the liquid that they're in with little bits of chemical or something. I mean, I don't know what, that's the way the brain does it, right?
Yeah.
Like, do something.
I'm not sure. I mean, we could have like thermal sensors on there. Everyone could slow down when it got too hot. That's probably a good idea. But yeah, I mean, there's lots of things. Again, you know, these are second order. Yeah. Let's see if we can do the first order thing first.
The interplay between the local and the global.
Yeah, I think that is interesting. One of the things that's actually very interesting about the brain is the amount of surface area there is, right? It's all folded up. And we could do something similar to that. There's no reason why we only have to have the outside be, you know, you can imagine you have fins that are providing something. And then the mean distance between people and the global communicate, because you can globally communicate to everybody on the surface at once, could be reduced. That might also provide other benefits for power distribution. I don't know how it influences the wires. But so there are other schemes that you could think of. Okay. So at this point, what do we have? We have something that's brain-like, I guess. I don't know. That's probably too strong, actually, but brain-inspired. So we have these 1 millimeter diameter units. They're running somewhere between 1 and 100 megahertz. If I'm using sort of stuff without lots of improvement in getting down to the sort of 1 picojoule range, they're probably running at 1 megahertz or less. We have a way to communicate and do power distribution, and these wires give us this sort of rich graph. Okay. We have about 256 gigabytes of memory, so you can see it's a terribly memory-poor system. This is one of the problems. Yes?
What frequency are you running over the wires?
I don't know.
You don't have any idea yet?
No. Close to DC.
Okay, so very low frequency.
Yeah. Well, no, I take that back. That's completely wrong. For doing power distribution, we're very close to DC on the order of kilohertz. Those things, I forget what we looked at the analysis, but on the megabit range, something like that. Again, that's a I mean, so in the SPICE simulation, it's sort of looking at, you know, whether this is physically possible. We need to actually build some of this hardware to determine what the interplay is between the amount of energy it's required, what frequency we can support, I mean, all that kind of stuff. Okay, so we have the key thing for me is that there's lots of connections. On the plus side, On the minus side, it's that it's very memory poor. So this is with thinking about SRAM, 6T cell SRAM, and if you really want low power, you might actually use more transistors, so that's a problem. If we look at DRAM, then we get, another factor of 40, so that's probably a good thing. Yes?
I lost track of the numbers. There were 6 wires per node.
Yes.
And each wire had how
10
many?
10 diameters. On the order of like 10 to the 5. Well, no, you can. So you can't do it that way because there's lots of overlap in these connections, right? So if you don't count overlap, it's on the order of 10 to the 6, let's say. But if you do count overlap, because they can go through 2 contacts, right? So you get that square effect. If you do count overlap, it's about 10 to the 5.
So that high number is taking advantage of the squaring effect.
Oh yeah, absolutely. Without the double hop thing, then you're limited to just your local neighbors, and it's not interesting. I mean, it's lots of neighbors, I guess, but it's not rich enough. Okay. Yeah, so I talk a difference between a hop, which is the logical A to B, and a contact, which is how, right, I'm saying you go through 2 contacts to do 1 hop. As many as, okay. Okay, by the way, so, if we think about scaling, just the general Moore's law thing, if we can, at the 22 nanometer node, what we do is we keep everything the same, but then we get petabytes. So that's how we can make up this balance. Or the alternative is, why don't we reduce the size of the nodes to 100 microns in diameter, and then we have maybe, let's say, 10 to the 12 nodes. I don't know whether you keep the wires in this case. This is just a whole different, regime, because if you wanted 1 micron voxels of the actual brain, the way they do things out in Zurich, I forget what the name of that project is. Oh, it's called Blue Brain, I guess. We could actually simulate a centimeter cubed of the brain completely at the molecular level with the 1 micron voxels. So it's a completely different tool, right? Because here you're doing physical processes, and really this was my original ideas were thinking about logical processes and doing AI, not the brain itself, but as a very detailed simulator. And the kinds of things that they do once you get the voxel size down to a micron cubed, you could do with these processors. So if you look at the kind of stuff they're doing at the Blue Brain project. Okay, and 10 to the 9 nodes, if I go back to the 90 nanometer scale, what is it? It's about $20 million. So that doesn't seem like a lot to me. And then once we figure out how to do it, you can get 10 to the 12 operations per second. That's a peta operation machine for something that you put in a Coke bottle, which is sort of a cool idea. So that's where the brain in the bottle comes from. Okay, so what I should just say, I have a little. I'm done in an hour. I have an hour, right? Okay, so I have I should speed along here a little bit. But one of the things that originally motivated me thinking about this was that I wanted to have an MREFC that was more interesting than just Internet 2. The MREFC is a sort of massive equipment grant that NSF does, like the Hubble Space Telescope, LIGO, the big ice cube down in Antarctica. An instrument for researchers in a field to study something. And I thought, right now this is research just to build this, but if we figured out how to do it, we'd have a tool that researchers could use that would be motivating to the guy walking on the street, right? I mean, Internet 2 is like, okay, I'm going to get less spam, but who cares? It's like plumbers, I mean, plumbing is important, right? It saved more lives than practically any other invention, but it's not very interesting. And if we want to get the best and the brightest to come into computer science, I think we need to get back to that state where we're doing really interesting stuff that captures people's imaginations. So that was my original thing. So I'd really like to have this sort of machine, but from a research point of view, I'd like to figure out how to program this darn thing. So let me talk a little bit about that. So first, let me just talk about the basics. I showed you the video of just everybody trying to send a message to everybody, but I didn't actually explain how we're going to route things in this machine. Okay. And remember, it's unbalanced. Lots of processing and communication, but memory poor. As a matter of fact, we don't have enough memory in the nodes, if you also want to do something else, to store a list of every one of your neighbors. So the traditional sort of, it comes in, I pick my neighbor that it should go to and send it to that neighbor. That's not going to work. So what do we do instead? Well, every node knows its XYZ coordinates. Okay, that's actually fairly easy to do. You can just run an algorithm knowing what the crystal lattice is and figure that out. And we'll basically do geographic routing instead of IP. So everybody gets this unique XYZ coordinate. Tells them where they are, and it also, if you're trying to route to somebody, you sort of know how far away they are. Right? So we're basically going to do geographic routing. And the thing that makes this interesting is that we're not going to store a list of everybody, but we're going to, sort of the setup phase is you collect the information about all your neighbors, and then you sort of divide up this sphere, you project everybody onto a sphere, and you pick log n points, log n, where n is the total number of nodes in the system, that sort of random, with some probability that tries to distribute these points around the sphere. So if I want to go in some particular direction, I know that I've got somebody that's close to that direction, and I can send it in that direction. Okay? And we did some, I should have put this graph in here, but how many neighbors do you need to pick in order to have a single connected component? Because you can imagine if you're only picking, let's say, 20 out of 100,000 neighbors, then you might end up with two completely separate graphs. But log n neighbors is enough to actually, we can't prove this, but empirically at least, it's enough to end up with just one connected component. Actually, you need many fewer than that. 6 or 7 neighbors is enough. Because everybody's picking a different set of random neighbors, and there's just lots of connections. Okay? So the routing algorithm itself is trivially simple. Okay? So I am at some location, and I'm routing to some other location, so I calculate the Euclidean distance, and I know what direction I basically want to go, and with a probability biased towards that direction, I pick a random neighbor. So I'm essentially flipping a weighted coin that's biased in the direction that I want to go. I don't always go in that direction. I might go in some other direction just to make sure I stay out of local minima. And then I route. And if you look at the way this is, this little function here, as I get closer, this is the distance between me and the destination, as I get closer, the weighting of the coin gets more and more uniform. So when I'm far away, I'm basically greedy. I pick the node I know about that is closest to the destination node. As I get closer, I'm likely to pick somebody off to the side. Okay? And when I get really close, I'm going to be completely uniform. Okay? So you say, well, look, I'm routing to somebody. The probability that one of its neighbors has that node on its list is trivially small. But remember that when I put a message onto a wire, everybody can hear it. Right? It's essentially I'm broadcasting to my entire neighborhood. So I'm sending a message to Simon. I want to send a message to Simon, but I don't have Simon on my list of neighbors, but I have Stuart on my list of neighbors. So I send the message to Stuart, and Simon is listening to it. Says, oh, that message is really for me. And then he grabs that message. So basically, you just put a time to live on this message, and after the message has been sent, once it runs out of its time to live, it dies. And if we make the TTL big enough, then we can essentially arbitrarily make the probability it gets delivered to the right guy as close to 100% as we want. Okay? So let me show you a little bit how that works. I think this is the right one. Yeah, I know. I just have to get my mouse over there. Okay. So what you see here is the destination node. So we're going to go to a destination, then we're going to go to another destination. So once we get there, and then here's a source, and there's a destination. And so these are the red nodes are the intermediate nodes that I'm going to, and the blue wires that you see, so the nodes have all been made to disappear here. The blue wires that you see are sort of the neighborhood that when I'm sending from one red node to another, the wires that sort of are getting that message. So all the people connected to that message can hear that message. Okay? And so for this million node brain, basically a TTL of 12 is enough to get us to wherever we want to go. Yes?
Was the wiring mesh that you're using here tuned with the prior algorithm? So you had one that was kind of doing this connectivity timing.
Yeah, it's the same brain actually.
Okay.
Or I don't know whether it's the same one, but the way we made it is the same. And
yeah.
We generate lots of these and run them over and over. Right? So this is the basic way that this works. And you can see that sometimes, first of all, it's hard to see because this is in 3D. So when you see two red dots very close together, you don't know whether that's on the z-axis. So there's just a lot of information here. I mean, if you look at it on the screen when it's running, you can tell. But sometimes you go a far distance, sometimes you don't go that far distance. And this has to do with the fact that you're only keeping 10 or 12 nodes, I think, in this, for this simulation. 10 or 12 of the 3,000 nodes that you can actually talk to on your list. Okay? Okay. So I just showed, whoops, I'm going backwards. I have it upside down. Okay, so why does this work? Well, one of the things is, and we're trying to actually understand this, is if you look, one of the ways to characterize the graph is sort of look at the eigenvalue gap of the normalized Laplacian. And if you really press me on this, I'm going to just say, speak to Felipe. But what I do know as a systems engineer is the closer to 1 you get, the better. And if you're sort of at 0.1, it's an expander. And we're at like, 0.9 here. Okay? So this is the number. So the way he calculated this is he picked a node. He looked at 50 diameters out of the node and grabbed that entire subgraph and then calculated the eigenvalue gap between the first and second eigenvalue. Okay? And so he did this for 50 nodes, and you can see most everybody is above, point whatever. This actually looks, I see. Everyone's above 0.99. Okay? And lots of people here are very close to, 0.996. That's huge. And that's basically what this means is that in that graph, to mix happens very quickly. You can do it in one hop, you can get basically anywhere. 2 hops, you can get basically anywhere. And so all these little subgraphs are what we're calling, local expanders. So, that doesn't really mean anything yet because the expansion property of a graph has to do with how it works when it scales. So we're trying to actually come up with a way of characterizing these graphs because they just work so well. Okay, basically, these are very rich environments, even to 50 diameters out. The wire is only 10 diameters. This is sort of a fairly big thing. And as we make the graphs bigger, it takes longer to calculate. These subgraphs bigger, it takes longer to calculate. So we're working on that. The actual eigenvalue gap for that entire million node brain is like 0.89 or something. I mean, it's still huge when you consider, that you're an expander if it's like 0.1. Okay. So, and the other thing to remember is that every transmission, every time you physically send one message, you're broadcasting to everybody. And this looks at the number of messages in that. So that video is an example of sending like 6 or 7 messages, and when we send like randomly, a couple million or 100,000, a couple million, I don't know, 10 times 10 to the 5. So that's 1 million messages. How many hops? This cumulative distribution graph of how many hops it took. So, like 99% or 95% of the messages, if we send it 20 hops, get delivered. Okay, so you set the TTL wherever you want it to be, and then that works. And this is just still the first naive implementation of this algorithm. So this will only get better, I would expect. Okay. So how would we use something like this? Well, one thing is we could do high-level simulations of the brain. We could look at really massively parallel algorithms. And then what I'm most interested in is what I'm calling massively connected algorithms that depend on a lot of connectivity. And then I'm not going to have time to talk about these query-driven workloads, but I'll talk about it offline. So, the obvious thing is you want to do something for massively parallel things. You want to do some huge video pipeline. You basically make every processor a pixel. They're all locally connected, and they're also and your pipeline just runs along this. The video comes in one face of this cube, and it comes out the other face. I mean, this is sort of an obvious use of this. But let's think about massively connected ones. These are algorithms that have a huge graph structure they work on. So, sort of paradigmatic of that would be, let's say, Pagerank. One way to think about Pagerank is you've got this huge graph, and you want to figure out, where people end up, what the stationary distribution is. And so, is there a way, we've got lots and lots of connections, we've got lots and lots of nodes, to essentially embed the internet on this machine, and a physical link on the machine is like a logical link, and so people are sort of close together, and we can just use the massive connections of the machine to implement Pagerank. Okay? So the first thing we have to think about is how do we take this graph description and embed it inside this system? Okay, because I can only stream it in through one face, and I've got to sort of get this completely distributed. The nodes have limited memory, so I can't remember the whole graph as it's coming in. I'm limited in my I/O to the surface, and I don't want to spend as much time sort of pre-processing the embedding as I do running the algorithm. So we abandon this idea of really trying to take advantage of the physical links and just use the fact that you don't have to spend many hops to get from any one place to another. And basically we said, well, how bad would it be if we take every URL and hash it to some XYZ location, and then that's where you put that page. So then the links are directly encoded. If I want to, I want to follow a link, I just calculate that hash, and then I go over to that place. Okay? And so this is how bad that is. So one of the things you have to think about is because it's not in a direct lattice, you might calculate a hash, and there's no node at that location. And you don't know how to do, what to do with that. So what we basically do is we say, okay, we calculate this hash, and then we try and get to that node, and we are going to try for a certain number of hops, let's say 20 hops. So we'll make the TTL 20. Okay? And then we just say wherever we ended up, that's the actual node that's going to take this. So like any sort of hash function, you've got to actually check to see whether the node has the actual URL or not. Then later on in the algorithm, when we want to go to this node, we say, I want to go to XYZ, but for this URL. And so as you're going, you're searching for that particular URL, not just that particular location, because the location might not exist. Okay, and you can see that this is the mean error in the number of diameters away we are from where we hash to. And so, lots and lots of these pages are, 2 or 3 diameters away. There's actually a whole bunch at 0. This is the standard deviation. You can see they're under 0, so that doesn't make much sense. But some of them are pretty far away, so you probably want to do this pre-processing step pretty long. Maybe you do 50 hops or 100 hops, so you can get closer and closer to where you're actually supposed to be. Okay? And then this algorithm is sort of is very simple on this kind of architecture that's so parallel in some sense. So the way PageRank works is you have these random surfers and you want to see who ends up where, right? And so basically with at every step in the algorithm, we start out with a certain number of surfers. So you move to some neighbor, meaning you follow some outgoing link on some page with some probability of 1 minus gamma, or you just jump to some random place with probability gamma. So that we don't have to actually jump to random places. We probably could. It's easier to just kill all the other nodes that we have and then rematerialize a certain number of nodes that will be the equivalent of them randomly jumping to you. Okay? And so, this is how we go to a random node in the graph. Okay? And so basically, it's a fairly simple algorithm. And if you want to discuss the bound on this algorithm of how far away from the actual page rank, I can do that offline, but I'm running really late here. So that's basically what I wanted to talk to you about today. And what we're thinking about mostly at this point is how we can program this thing, make sure the basic physical principles make sense, and we're going to start thinking more about how to build it, depending on whether I can get a student that's really interested in that or not. And so that's what we're trying to work on. I should say that right now we're sort of improving the simulator for larger systems, and we're actually implementing the PageRank. We have various of these routing protocols implemented on our simulator so we can actually study them, and we're thinking more now about the actual node development. One of the things I'd like to do, and this is for multiple reasons, is build a 1,000-node machine that actually uses this. It wouldn't be nanoscale, these wires, but uses the same basic principle just so that we can actually have a real physical system that we can show what we're doing. It's sort of an interesting price point, and it turns out that this kind of machine, this sort of very cheap machine, you notice this 4 gigabytes of flash, that's because Dave Anderson has some interesting ideas of how to use a machine like that for doing high query throughput processing. It's very economical in some sense in terms of the amount of power and stuff that's required. So that is what we're up to. Sorry it took so long. Are there any questions that people held? Yes?
So do you feel that it's better to have sort of, I would say, non-deterministic storage in terms of, similar to our brain, the information is fairly distributed, we don't know where a particular bit of information, right? And it seems like with your hashing example, that's kind of what you're using, which makes sense. But of course, the penalty we as humans pay in this case is that sometimes our recall is extremely slow, right? Because we're kind of doing this, although it's parallel, but it's a search of a tremendous amount of information, right? So do you feel that this is kind of a trade-off you have to make in this architecture? Or is it that, does it make sense to introduce deterministic storage in order to speed up access? Or what's your take on this?
So my take on this is that the hashing thing is really easy for us to do and understand, so that's why we're doing it first, but it's not the right way to do it. That's just my gut feeling. I don't know, maybe it is. It's so easy to implement. I don't know how much we're going to actually pay for this versus deterministically going to some node and looking it up. Because I don't know how we get back which nodes are where exactly, given the sort of, I mean, you can see we're handicapped by the memory limitation, the fact that the machine is unbalanced. And maybe that's something we need to address architecturally. But right now, I've been pressing hard to make all the sort of algorithms memory impoverished.
Because this is interesting, because this really seems to get back to the same issue in massive parallel machines, which is, do you want locality and speed of access, or would you rather have this tremendous addressable, memory, but at the same time you pay a latency penalty? And the trade-off is a little different here, but it still kind of has that feel.
Yeah. I mean, it is just a massively, massively parallel machine. It's a different kind of space, right? You're going to want to harness the network volume, the message volume that you have in this machine. I don't know exactly what the best way to do that is.
You want to use the structure of your brain has been made from years and years of evolution, so wouldn't you want to try and copy what the brain does as much as you want? Why would you want
I don't make any claim, even though I use the word brain a million times, is that this is anything at all like how the brain works. And generally, I'm philosophically opposed to sort of biomimetic approaches, right? In other words, there are no birds that fly at Mach 2. Nature just doesn't go there, and so I'm interested in that interesting space. I mean, yeah, we can borrow and be influenced by it, but I wouldn't try and copy the structure, for instance. So, I mean, the research issues here that I'm trying to explore, sort of stochastic assembly, what does that mean? Can we harness it? Is it useful? Yes?
So, all right, I know you're not trying to mimic the brain, but I still want to ask the question a bit about the brain, which is, this is all totally stochastic.
Yes.
Any given realization will be totally random networks connections. If you take two brains, how much of it are they stochastic?
Really good question. I do not know the answer to it. That's I think there's certainly some areas that aren't that stochastic, like the visual system. It's pretty much the same to everybody. I mean, they're obviously not identical, but the general architecture is certainly. I don't know how, if you took 1 million brains and you tried to do a model of where you would expect the nodes to be, what the sort of distribution would be. Would it be tight or loose? That would be interesting. I'm sure people have looked at it. Actually, I don't know if people have looked at that. Probably just not enough
There's some
data.
general assumption of that, I think, but it's...
Has it been tested?
I don't know how deep it's been tested. I know around, in brain surgeries, for instance.
Yeah.
They'll look at a person's brain, and most of them are pretty similar.
Oh, certainly we know that the high-level architectures are very, very close.
But then they go in and, if they're actually going to do something, they think, okay, let's go probe this and see what's really going on there. So it's a question, I think, of how much is influenced by...
Yeah, I mean, we all have different fingerprints. Is that stochastic or not? Yeah. Right? We all have fingerprints. I mean, so I think probably there's no identical places where the wires are, but it's something a little bit bigger than single neurons. There's a lot of similarity.
Take that to another level. One of the things I looked at when I was in college was basically disconnection syndrome. Or when very young children that have epilepsy, very severe epilepsy, or damage to one part of their brain, they can actually go in and remove an entire hemisphere. Okay? And your brain's crossed over, so you'd think they'd lose motor function. If they do this early enough, that maps to the other hemisphere, and essentially they grow up with very little cognitive deficit. Yeah. So there's a basic layer that's laid down during development, but it can be highly influenced during development and after childbirth.
Yeah, but so the development of the brain, I think, is not, childbirth is not a good place to draw the demarcation there, right? So that's the other issue.
Yeah, but as the child grows up, there's a very plastic element there.
So I'm going to make a shameless plug for my talk tomorrow. Okay. I'm going to talk about programmable matter, and this is just a video some people put together. Imagine that this is, each one of those little particles is a processor. So they're doing some 3D modeling here. But I'm happy to answer questions about the brain in the bottle, too. Yes?
One more question. Yeah. Why did you go for a 3D thing, like with the computational power of the 3D cube? Instead, if you had taken, let's say, something five nodes deep and a large flat thing.
Yeah, so I mean, this is, again, you know, my bent is towards trying to understand stochastic processes, but why not just take the whole damn wafer, make tiny little processors, have lots of wires between everything on the wafer, and just make a stack of these things, right? And then pump fluid through it. Seems like, I mean, that would be interesting, and maybe that is the right architecture, but I don't know how you make connections between the wafers.
Well, I'm thinking you throw them down, but you throw them down in a dish rather than in a cube.
Oh, well, the cube root is better than the square root. That's why, for the 3D stuff. Yeah.
On a similar line, why these sphere things? Like, you could just have a whole bunch of flat things that are just thrown in a pile that would kind of, like,
how do you get the wires,
that would be kind of all meshy.
So you want to, it's a square die with the wires attached.
Or just like a long, maybe like a long strip, a bunch of long strips so they kind of fall in all kinds of directions, not just flat. And then, I don't know, with the wires.
Oh, I like that, actually. That's sort of a good idea.
Processor and the wire kind of become the same thing.
Well, you could still have the wires, but...
Yeah, but you have fewer wires, and this wiring along the thing becomes much higher bandwidth. I don't know. That's an interesting idea. Yeah. I mean, here's the way I'm thinking about it, is that I want the processors, so partly it's this, you know, this video describes why it is that I want the spheres. Because if I can get this thing to work and NSF decides to like fund building 1 billion of these, then this Claytronics stuff will happen by magic. So I have an ulterior motive. But the issue that I've been thinking about with all right, so with any 2D thing, I don't know how I get the wiring in 3D, and I think I want to get that cube root advantage. And I mean, the idea of making this strip with a, like maybe it curls up a little bit, you drop the strips in, that's sort of an interesting idea. I want the nodes to be really simple and think about them as a synapse.
Are the spheres, I mean, they curl up, are they actually strong enough to support the weight of the things above them, or will they just smush down?
Well, the process is a little more complicated than that. You can think of them as glass beads. So we're going to do something to that, actually make it solid. So there's fluid not running through it, for instance.
Yeah. Well, the fluid's going to give you some buoyancy and support there too, I would think.
Yeah, but I mean, it's like a piece of glass, or a piece of sand.
Up, but then you do something that forms like.
And actually, we're not thinking about curling it like this. We're thinking about like taking a Mercator map projection, so that when you fold it up, it's actually almost 100% of the surface is used. That was just an initial. I'll talk about that more tomorrow, too, actually.
A more mundane question. How are you doing in seeking funding for taking the work forwards?
I'm having a dry run on getting funding right now, so I don't know.
Well, what's your scaling? What do you think you need to do to get to that next
I think building this down, you know, people, almost everyone in the United States is from Missouri, basically. I think building this machine would be very useful, but I think maybe I don't know. I might not be the right guy to fund the next step if it's not at an architectural level. I might be a chemist, for instance. But you know, I think also, as we can show, at least in simulation, that the algorithms are interesting, then you know that's also part of the next step. So I think another, year of simulation and algorithm development was fruitful. Meanwhile, there's this thing going on with the CCC. So, and we have enough data to motivate that. And so that's the important thing. That was sort of the important thing. So it's a very indirect kind of process at this point.
There's no question.
If you could tie your thing to cryptography, like breaking cryptography, you could tie your other thing.
I don't know how much connectivity you need for that. You just need massive parallelism. On the other hand, they just want to dump those things in a big box, locally connected. It's probably good enough. That would be much easier to build.
Okay, so let's wrap it there. Tess around for the next couple of days. He's pretty busy with meetings, but there is some time available if you do want to have any in-depth conversations with him. I'm sure he'll be open to dialogue over time. He's very passionate about this work, and I think it's fascinating myself. So thanks very much for coming today. Thanks.
Thank you.